I'm just going to be going through problems from the midterm review. I'll post a lecture. It's supposed to be like Monday's lecture that you can watch over the weekend. As homework, you'll go through sections, I think 6.2 and parts of 6.4. But that's kind of like right now your focus should be doing the midterm and not like learning new stuff. Okay. So without further ado, let's go through the midterm, and then I'll pass out. You have 2 homework assignments I need to pass back out, which I'll do at the end of class with like 5 minutes left. Okay. So are there any, I guess I'll just open the floor to any questions people might have. Are there any questions people want me to go through specifically before I just choose problems to go through? Yeah, Seth.
2.
Problem 2. Like 2A or 2B or
2A.
Okay. Yeah, so 2 is one of these problems where you have to do projection. It's like a section, I think it's 4.3 when you're doing the least square solutions. So for problem 2, well, let me just read it out loud first before I write down the setup. So for problem 2A, it says, for the following problems, find the equation of the least squares line associated with a given set of data points. So we're given 2 data points, 6, 3, and minus 2, 0. And we want to set up a system of linear equations that we can then, I guess, like approximate a solution using this least square solution. And then we'll end up getting the equation of a line that serves as a best fit line for the set of data points that we have. So summarizing what the problem wants, it wants you to find the best fit line for 2 data points. The 2 data points are 6, 3, and then minus 2, 0. And so we have the following system of linear equations that we want to solve, represented in matrix form as the following. So the first column is just going to be given by 1, 1. The second column is given by the x components. So it's going to be 6 in the first row of the second column, then minus 2. So you have 6 minus 2. And then you multiply by some 2, 1 vector, which you could call like xy, but I'm just going to call cd, keeping in tune with the notation used in the section. And then this is going to be equal to another 2 by 1 vector, where the 2 by 1 vector is given by the y component of the data points that you have. So it's going to be 3, 0. So it comes from these 2 points or components. And so this first matrix I'm going to denote by A. The second, I'm just going to denote by this vector x. And then this is going to be denoted by B. And so from section 4.3, we know the least square solution is going to be given by the following equation. So this is what you need to remember if you want to be able to solve these kinds of problems. If it shows up on the exam, for instance, it's given by x. It's usually denoted by this x hat, say like a caret over the x. And it's going to be given by the formula A transposed times A inverse multiplied by A transposed multiplied by B. So it's a matter of finding this matrix multiplication, right? We are multiplying 4 different matrices. You just have to multiply them correctly, which is maybe easier said than done because you have to do A transpose times A and find the inverse of this and multiply by A transpose. If you had a problem like this on the exam, I'll just give you what this matrix ends up being. Just because this is kind of like chapter 2 stuff, is knowing how to compute this. But just writing things out, making clear, we have A transpose is equal to 1, 1, 6, minus 2, right? So the first row, or first column becomes the first row, second column becomes the second row. That's A transpose, and then A is just this matrix here, 1, 6, 1, minus 2. So if we multiply these 2 matrices together, we end up getting A, the T was a little too low, A transpose times A inverse. This will be equal to the inverse of the matrix 2, 4, 4, 40. kind of looks like a 6. So we want to find the inverse of this matrix. We don't need the parentheses. It's just the product of this matrix with this matrix. And so I guess this goes into another problem. I think it's like problem 7 or 8 from the review, where it wants you to compute the inverse of this matrix. There's an easy way of computing the inverse of a matrix now that we're familiar with the determinant. I'm just going to write this down so that way it's like technically I'm reviewing another problem on the exam review, so I feel like it's worth doing. So as a reminder, if you're given a matrix A inverse is just given by 1 over the determinant of A multiplied by, I guess let me write this out first. So I need to actually say what A is equal to. So A is just like a general like A, B, C, D 2x2 matrix. So if you have a general 2x2 matrix and you want to find its inverse, what you do is you swap the 1, 1 and the 4, 4 entry, and then you multiply the 1, 2 and 2, 1 entry by -1. So you don't have to go through with row reduction to find the inverse of this matrix. Just so that way, if something like this does show up on the exam and you need to find an inverse, you want to use this determinant method, not like this row reduction, And so this tells us that A transpose times A inverse, this is going to be equal to 1 over the determinant of this matrix. So the determinant is 80 minus 16, which is equal to 64. And then this is going to be 40 minus 4 minus 4, 2. So that's an easier way of computing what this inverse actually ends up being equal to. If you distribute, you can write it in the following way. So it ends up being equal to 5 over 8 minus 1 over 16 minus 1 over 16, and then 1 over 32. Okay, so this is A transpose times A inverse. And then from there, it's just a matter of computing or multiplying A transpose times A inverse times A transpose times B. And so I guess going back to the beginning, we have this least square solution is going to be equal to this matrix I have written above, this 5 over 8 times minus 1 over 16, minus 1 over 16, then 1 over 32, multiplied by A transpose, where A transpose was this matrix 1, 1, 6, minus 2. And then times B, where B was equal to 3, 0 up here. So it's a matter of multiplying these matrices, which I'm just going to look at what I already have written because this looks like it'll be a mess to deal with. So this ends up being equal. If you multiply these 3 matrices out, you end up getting 3 over 4 and then 3 over 8. And so what this implies is that the least squares, so from these two, like this x component here, this y component here, you can determine a line where the slope of the line is given by the y component, and then the y-intercept is given by the x component, right? So you end up getting the following line: y is equal to 3 over 8x plus 3 over 4. Okay, so that'd be the solution to this problem. And then problem 2b is very similar. There's just more data points. I think you have 2 data points instead. But in the process is the exact same. It doesn't really change at all. Okay, any questions about 2a? Yeah, so the main thing you need to know, I mean, it's all just computation aside from knowing that you have to compute this product in the first place. This is like the key thing to remember. And I feel like for this exam, I feel like I want to say, I need to make a decision. I'm thinking like whether or not you should be able to use like an index card. I feel like I'm seeing nods. I'm like easily susceptible to pressure. So I don't know. I feel like we can probably do index cards, just like a 3x5 or something like that. But I feel like the only equations that are, I think this is kind of like this equation's hard, and then there's like the projection formula in general. It's like, and it's a little bit unintuitive, hard to remember. So yeah, you can use like a 3x5 index card. Okay, any other questions about the least square solution stuff? Okay. Let me make sure I'm recording. Okay. Okay. What other questions do people want me to go through? Yeah, Izzy. 9? 9 from not like the true and false 9, but yeah. Okay, so for number 9, let me highlight it so it's down here. Oh, that's a true and false 9. So for this 9, it wants you to find the eigenvalues and eigenvectors of the following matrix. So part A, it just wants you to find eigenvalues and eigenvectors of this diagonal matrix A, where you just have 5s along the diagonal. And then part B wants you to show that the eigenvalues of an upper triangular matrix are exactly the entries along that diagonal. So I think part B is a little bit more difficult than part A. So this is 9. And we have A is equal to 5, 0, 0, 0, 5, 0, 0, 0, 5. And so we know that the eigenvalues, this is just general review that you need to know from section 6.1. So eigenvalues are the solution to the equation. So if you take the determinant of A minus lambda I, the eigenvalues are the solutions of this determinant, right? You set this determinant equal to 0, and then you solve for the eigenvalues. So they're the solutions to this determinant that you want to solve. So for this one, this part really isn't going to be so bad because we just have a diagonal matrix. So the determinant is just going to be the product along the diagonal. So if you consider, there should be, now that I've introduced determinants, I always do that now. So this A is just like a matrix, but we're going to be thinking about the determinant. So if we think about A minus lambda I, this is the determinant of 5 minus lambda, 0, 0, 0, 5 minus lambda, 0, 0, 0, 5 minus lambda. And so because it's an upper triangular form, in fact, it's diagonal. So the determinant of this matrix is just going to be 5 minus lambda times 5 minus lambda times 5 minus lambda. So this is going to be equal to 5 minus lambda cubed. And if we set this equal to 0, this will imply that lambda is equal to 5 is our only eigenvalue. The only solution to this equation that we have from taking the determinant. And so, and it's talking about it wants you to find the eigenvectors as well. So I think like the main thing you need to realize, so this gives you exactly what the eigenvalues are going to be. To determine the eigenvectors, what you do is you find the null space of A minus 5 times the identity. And you can see that this is just going to end up giving you the 0 matrix. So I guess the next thing, so if you want to consider eigenvectors, it wants you to find the null space. Like whenever it's asking you to find eigenvectors, you should always think like we need to compute a null space. So we want to find the null space of A minus 5 times the identity, where 5 is the eigenvalue that we have. That's why it's A minus 5I. But then you note that A minus 5 times the identity, this is just equal to 5 minus 5, 0, 0, 0, 5 minus 5, 0, 0, 0, 5 minus 5, which is just the 0 matrix, right? And so if you want to find the null space of A minus 5I, what's the 0 matrix? So it has a 3-dimensional null space because we don't have any free columns. So the null space is just all of R3, right? So we have null space of A minus 5I. This is just equal to R3. And so a basis for the null space, if you just think in terms of free variables, we have a free variable x, free variable y, free variable z. And like the corresponding basis for the null space will just be the vector 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Because there isn't any sort of like relations we have, because we just have the zero matrix. So we have like basis is 1, 0, 0, 0, 1, 0, and then 0, 0, 1. And so these are the eigenvectors. Oh yeah, this one is like a little bit tricky. I mean, finding the eigenvalues isn't bad, but it is kind of like a weird situation where you do the subtraction, you just get the zero matrix. But if you just think back to what we know about null spaces, you can determine what the answer is going to be. Right, the eigenvectors are just the basis of the null space for like A minus lambda I. Okay, any questions about 9a? Oh yeah, easy.
So why is it not like 0, 0, 0, 0, 0? Like, is zero vector for basis?
For this, like, what we're doing is we're finding the null space. Like, if we want to find the eigenvectors of a matrix, what we want to do, like corresponding to an eigenvalue, is we're considering A minus 5i, this matrix here, and we're finding the null space of this matrix. And so if you look at this matrix, it ends up being the identity matrix, or not the identity, it ends up being the zero matrix, which means that, like, thinking back in terms of like the relationship between the dimension of the column space and the dimension of the null space, we have like none of these terms are non-zero. So we don't have any rank. Like this is a rank 0 matrix, but we have 3 columns. So we have that the null space of this matrix should be 3-dimensional, right? So the null space of A minus 5i is going to be 3-dimensional because it's just the 0 matrix. You can also think in terms of if you multiply this matrix by any like vector in R3, you're just going to get the 0 vector. So that means like the null space is just all of R3. So you should have 3 non-zero vectors which serve as the basis for the null space, because null space is 3.
5, 0, 0, or 0, 5, 0, and 0, 0, 5. Is that something you started with? Or?
Yeah, I mean, either way. I mean, this is it will determine the same space. At that point, it's just like multiplication by a scalar, so it would be fine. You're allowed to make those adjustments. So it'll span the exact same space at the end of the day, and they're still linearly independent. Yeah, but the main thing is we have this matrix, and we want to determine the null space. It's just the 0 matrix, so the null space is going to be 3-dimensional because we have 3 columns and we don't have any rank. And we have to have that rank plus the dimension of the null space is equal to the number of columns. So maybe I should just putting that into words very briefly. So like the rank of A minus 5i is equal to 0. So we must have the rank of A minus 5i plus the dimension of the null space of A minus 5i. This has to be equal to 3, which implies the dimension of this null space has to be equal to 3. And so the eigenvectors are just the basis of this null space. So it's a 3-dimensional basis. And it's just, the null space is just R3. So, okay. Any other questions about 9a? That's a little bit tricky. And then 9b, it wants you to do the following. So 9b, it wants you to show that the eigenvalues of an upper triangular matrix are exactly the entries along the diagonal. So I think like the best way of thinking about this, I mean, it really just plays into what we already know about determinants. We know that if you have an upper triangular matrix, the determinant is just going to be the product along the diagonal. And so if you just considered a matrix, I'm going to write out like a general n by n matrix. This might be a little bit messy, but this is like A, 1, 1 minus lambda. Beneath it, you have 0. You have like A, 2, 2, minus lambda 0, 0, 8, 3, 3 minus lambda 0, 0, and so on and so forth. I'm like always really bad at writing these like general n by n matrices, but above this diagonal, it doesn't matter. We just have like some entries. They could be 0, they can be non-zero. It doesn't matter. This goes all the way down to a n n minus lambda, and then you have 0, 0, 0, 0. So this is an upper triangular matrix, right? And so if we compute the determinant, so this is our a minus lambda I, or this is the determinant of some like a minus lambda I, where a is some random n by n matrix. If you considered what this determinant would be equal to, we know the determinant is just going to be the product of all these terms along the diagonal. So this is going to be equal to a11 minus lambda multiplied by a22 minus lambda multiplied all the way up to a n n minus lambda. And so then you set this equal to 0 and you find the solutions to this equation. But then you'll notice, like if you let lambda be equal to a11, this whole thing would be 0. If you let lambda be equal to a22, it would be equal to 0 all the way up until lambda is equal to a n n. So this implies that the eigenvalues are a11, a22, a33, up until a n n. It might be easier to write this out as like a 3 by 3 matrix, in which case it would just be like this guy here. And just take the determinant and you'll see like it's going to be 0 exactly along the diagonal entries. Okay, any questions about part B for problem 9? Okay, and again, it really just comes from the fact that the determinant of an upper triangular matrix is just the product of the diagonal entries. That's all we're making use of here. And the definition of the eigenvalue, I guess, as solutions to this determinant. Okay, what other questions do people want me to go through? Let's see. I feel like it's worth going through like a Gram-Schmidt problem. Like Gram-Schmidt is like one of those problems that's like guaranteed to show up on the exam. Okay, and I'm not gonna make it to like part B. Oh, I don't know. I don't know how I'm gonna do the Gram-Schmidt problem. I feel like I should have 3 vectors, but at the same time, it feels like it's too much computation. So I might do something in between somehow. Okay, so for problem 1A, it wants you to use the Gram-Schmidt process to determine an orthonormal basis for the subspace of Rn spanned by the given set of vectors. So I'll just go through part A, then part B is pretty similar, except you just have to do it one more time. So for part A, we have V1 is equal to 1, 2, 3, and then V2 is equal to 6 minus 3, 0. And so if we want to use Gram-Schmidt, let me just write these vectors down so I don't have to scroll up a bunch. So this is 1, 2, 3. And we have V2 is equal to 6 minus 3, 0. And so what you need to do with Gram-Schmidt is you're going to take these 2 vectors, which we can see are linearly independent, right? V2 is not a scalar multiple of V1. And we want to construct a vector or a set of vectors that are orthogonal to one another and are also going to be length 1 as well. So the first thing you want to do is make sure you construct a vector that is actually orthogonal to V1. And then afterwards, I just make it so you divide by the length of the vector when all things are said and done. I feel like it's usually more hard, like it's more difficult to work with like the unit vectors because then you have like fractions that show up. Okay, so the first thing we do with Gram-Schmidt is we just take our original vector, V1, and we don't do anything with it. So I'm going to define E1. This is just equal to V1. So I'm going to denote the collection of orthogonal vectors as E1 and E2. So that's why I'm writing like E1 is equal to V1, even though it seems kind of superfluous. And so we don't do anything with E1. Eventually we'll divide it by its length, but we'll keep it as it is right now. And then E2, this is going to be given by V2 minus E1 transposed times E2 over V2, I mean to say, over E1 transposed times E1. And then you multiply by V1, so, or E1. And so it's just a matter of computing what this is going to be equal to. It looks like a lot, but I think it's easiest to think in terms of, we're taking, this is really the dot product of V1 and V2, which is pretty easy to compute. And then you do the dot product of V1 with itself. So this part looks scary, but you're really just doing a dot product over a dot product. So writing things out explicitly, we have V2 is equal to 6 minus 3, 0. This is going to be minus, so the transposed of E1 is this going to be 1, 2, 3. This is being multiplied by V2, which is 6 minus 3, 0. So you can see what I mean, like this is just the dot product. If you think in terms of matrix multiplication, it just ends up being the dot product. And then in the denominator, it's really just the length of the vector squared. So this is 1, 2, 3 times 1, 2, 3. And then this is all times 1, 2, 3. So this should always give you a number, like it'll give you a scalar to multiply V1 by, and then you subtract that by your V2. So this will be equal to 6 minus 3, 0. Oh, and I guess this ends up being, maybe this isn't an interesting problem, because if they're already orthogonal to one another. I didn't even notice that. Like if you do like this vector dotted with this vector, you end up just getting 0. So they're actually already orthogonal to one another, which kind of makes it so this isn't very interesting, but whatever. And then you multiply by this, and you see you actually just end up getting V2 back again. I guess it shows it was worth doing in the sense that it's like reviewing what the equation tells you, and it shows if they're orthogonal, you end up just getting whatever your V2 was back, right? The next one, I guess, is a little bit more interesting, but okay. So we have that E1 is equal to, I mean, it just ended up being the exact same set of vectors over again. And then this is E2 ends up being equal to 6 minus 3, 0. So once you have this collection of orthogonal vectors, so these are all orthogonal vectors, what you want to do afterwards is you want to create a new set of vectors or list of vectors, which are just these two vectors divided by their length, right? So we're going to define, so now we're going to do unit vectors. To get a unit vector, we're going to define Q1, which is equal to E1 over the length of E1, right? So this is going to be 1 over the length of E1 times 1, 2, 3. And so this is going to be equal. So the length of E1 is just going to be, I guess it's been a while since we talked about this, but it's going to be the square root of 1 squared plus 2 squared plus 3 squared times 1, 2, 3. And so this is going to be equal to 1 over the square root of 14 times the vector 1, 2, 3. So this is our first vector in the orthonormal basis. So that's going to be one of our answers. Then the other is just going to be Q2, which is derived in a similar way. So this is going to be E2 divided by the length of E2, where the length of E2 ends up being the square root of 45. So this ends up being 1 over the square root of 45 times 6 minus 3, 0. So this is the other vector in our orthonormal basis. And this is where the problem ends. It just wants you to find an orthonormal basis using the Gram-Schmidt method. And so problem 3 or problem 1b is similar, except you just have more vectors. And I guess it's more interesting because the vectors aren't already orthogonal to one another. Okay, any questions about problem 1a? Okay, what time is it? We still have 18 more minutes, so we have a decent number of problems we can go through. Before I choose another one, is there a problem people want me to go through? Yeah, Sam, or were you raising your hand? Yeah. Okay, you say 8? Okay. Problem 8, not the true and false 8, just like the one where you write it out. Okay. So for 8, it wants you to show for, let me showcase it first. So for 8, it wants you to show for any matrix A, the row space of A is going to end up being orthogonal to the null space of A. So this is from section 4.1. You actually see it in like the 4.1 notes, but I felt like it was a good thing to review. So the important thing, it's like really just making sure you understand the definition of what it means to have like the row space and the null space. And so just writing things out in words, like we have that the null space of A consists of all vectors X such that we have that AX ends up being equal to 0, right? This is just the definition of the null space. It's a collection of all solutions to the system of linear equations, setting it equal to 0. And so if you rewrite this equation, like this AX is equal to 0, you can really think, like you can express A as a bunch of rows, right? Like it's just like row 1 over row 2 over row 3, so on and so forth. So this is really like row 1 of A. This is over row 2 of A. And then let's say like row N of A. And then this is being multiplied by this vector X. And this ends up being equal to 0, 0, all the way down to 0. Right? This is just rewriting this equation in terms of the rows of A times X, and then this ends up giving you the 0 vector. And so what this is really telling you is that the row 1 of A dotted with X, this has to be equal to 0, right? We're looking at, if we want to determine this entry here, this is going to be obtained by doing the multiplication of row 1 of A with X, which is really just the dot product of row 1 of A with X. So we see this ends up giving you 0. And then it's the same story for every single row. To get this entry to be equal to 0, it implies that row 2 of A dotted with X is equal to 0. Dotted with X, this will be equal to 0. And then goes all the way down to row N of A dotted with X, ends up being equal to 0. So what this is really saying, thinking back to what it means for two vectors to be orthogonal to one another, for two vectors to be orthogonal to one another, their dot product has to be 0. And that's exactly what we're saying here, right? Like we're saying row 1 of A is orthogonal to X, row 2 of A is orthogonal to X, row N of A is orthogonal to X. In other words, the rows of A are orthogonal to any X in the null space of A, because X wasn't anything special. X is just an element inside of the null space. So for any X inside of the null space, you'll end up getting these equations. And then you just have to think, like, what is the basis of the row space? A basis for the row space are just the rows of your matrix, right? Or it's like the row space just consists of linear spans of your of the rows of your matrix. And so if all the rows end up being orthogonal to X, it means that the row space has to be orthogonal to X. So this implies that the row space of A is orthogonal to the null space of A. Yeah, so I'd say this is actually kind of closer to like a chapter 3 problem, aside from the fact that we introduced this orthogonality idea for vector spaces in chapter 4. But most of it just comes down to interpretations of what it means to have a row space, what it means to have the null space, and how do they interact with one another. Okay, any questions about problem 8? Okay, what other problems? Yeah, Izzy? Mm-hmm. 7 true and false. Oh yeah, this is a property that I kind of make use of a lot in the true and false. And I'll say on the exam, there'll probably be a true or false where I have to make use of this property as well. I haven't written the exam yet, so I'm saying like probably a lot, which means that it probably it will probably make it onto the exam. So for problem 7, true or false, it asks if A is an n by n matrix with real entries, then the determinant of A squared cannot be negative. And I guess with the true and false, maybe I should label like this. Okay, I guess before I give the answer away, are there any ideas about whether or not this is going to end up being true or false? Does anyone know? Yeah. Do you know why?
I computed like A, B, C, D, that matrix, and I like squared it off. And then I saw like the highest power of like.
Yeah, I think that would work. Yeah, I think that's one way of doing it. I'll suggest like this is like what you really yeah, so you could compute it by just squaring A. So I'm not going to go through with this computation. But you'll get like a bunch of squared terms, which I think will eventually show like it's going to end up being like non-zero or greater than or equal to 0. The way I would recommend doing this is you want to make use of the following property. So this is the key property, and you're going to have to use it on this exam. If we're considering the determinant of A squared, actually, before I even write out what the answer is going to be, in general, we know the following. So if we have 2 square matrices, A and B, we have the following property with the determinant. This is going to be equal to the determinant of A times the determinant of B. So once you know this property, this is the answer to this is actually pretty straightforward, right? Because then what you can do is you can split up, like this determinant of A squared is really equal to the determinant of A times the determinant of A, which we can then split up as the determinant of A times the determinant of A. And so this ends up being equal to the determinant of A squared. And so this was why I specified that A is an n by n matrix with real entries. If it were complex, this could still end up being minus. Like if this determinant ended up being I, have like I squared is equal to -1. But because the entries are real and we have a square, this has to be greater than or equal to 0. So this is the key property you want to remember. There'll be a true or false question where I have to make use of this on the exam. I'll say it definitively. It'll show up. And I think it shows up a couple of other times on this on the exam review. I don't remember where exactly, but take my word for it. It shows up again. Okay, any questions about 7, true or false? Okay, and I guess as a reminder, I'm not going to go into detail about this, but I mentioned this in class before. You need to make sure you also know what happens if you do like the determinant of A plus B. Does this end up being equal to the determinant of A plus the determinant of B? I mentioned this in class, and I made like an example that was either like against it or for it. So it'd be worth reminding yourself of this before the exam. Okay, what next? We still have enough time to maybe go through one more problem quickly. Is there another problem people want me to go through? I think for the sake of time, I'll just go through problem 9 of the true and false. I think it's one of the harder true or false problems. And I'll go through it quickly because I need to pass back the homework or the last 2 homeworks. I want to make sure I'm not holding people over. So for 9 true and false, it asks any linear combination of a set of eigenvectors with shared eigenvalue lambda of a matrix A, or again, an eigenvector of A with eigenvalue lambda. Okay, and so what we're going to consider is we're going to let V1, V2, all the way up to Vn be eigenvectors of A with eigenvalue lambda. So they all have the exact same eigenvalue. And so what we want to show that any linear combination of these vectors ends up again being an eigenvector of lambda. At least you want to see what ends up happening. So we want to show that C1 V1 all the way up to plus Cn Vn is an eigenvector of A with eigenvalue lambda. So this is pretty much saying that the eigenvectors with a shared eigenvalue form a subspace. They're closed under linear combination, which would be a useful information to have, right? Then we can have like an eigenspace. So what we need to show is, or what we're going to be interested in is we want to take A multiplied by C1 V1 all the way up to Cn Vn. And we want to show, maybe I should have chosen a different problem. This one it's not going to take that much time, but it's like a lot more writing than I wanted to do. We want to show that this ends up being equal to lambda multiplied by C1 V1 all the way up to Cn Vn, right? If this were the case, this vector would then be an eigenvector of A with eigenvalue lambda by definition. So we're going to investigate what happens on the left-hand side of the equality and see if we can somehow rewrite it and turn it into the right-hand side of the equality that we have. And it's pretty straightforward if you just follow your nose pretty much. Right, so if we have this quantity, what we can do is we can distribute the A to each term of our sum. So this is A, C1, V1, all the way up until A, Cn, Vn. Cn, like the Ci's are just scalars, so you can move them in front of the A. So this is C1, A, V1, plus Cn, A, Vn. And then we know that A, like each of these V1, V2, Vn, all of these VI's are eigenvectors of A with eigenvalue lambda. So you can rewrite each of these multiplications as this being lambda multiplied by VI. So this is really equal to Ci or C1 times lambda V1 all the way up to the Cn lambda times Vn. And so on each of these sums, we have a lambda that we can then factor out. So this is going to end up being equal to lambda times C1 V1 all the way up to Cn Vn. So this is exactly what we wanted to show. We showed that A multiplied by this vector, where the vector is a linear combination of these eigenvectors, ends up being exactly the same as lambda multiplied by this vector. So this implies that this linear combination is an eigenvector of A with eigenvalue lambda. So this is the main equality that you want to show. Okay, I would probably write more if I wasn't rushed for time. Are there any questions about this problem? Okay, so I'll post the solutions to the rest of this exam review in a couple of